Hey guys, it's Miss Rainey. Today we are looking at excess limiting stoichiometry and percent yield and percent error. Let's get started. So excess limiting stoichiometry is stoichiometry when you have two different reactants so that one's going to get used up and another one of them is going to be left over. So we're looking at two different reactants and only one product. But just like any other kind of stoichiometry, we need to start with a balanced reaction. And we're going to look at the mole-to-mole ratio in a balanced reaction. So the first thing I'm going to do with this sample problem is try to find a balanced reaction, and then I can work the stoichiometry. So let's see. How many grams of silver will be produced? So if I'm going to write a reaction, silver is going to be on the product's side of that reaction. Produced from the reaction of 25 milliliters of 0.35 molar silver nitrate, that's AgNO3, with 0.5 grams of pure copper 2 pellets, that's just Cu. Notice my problem doesn't give me my other product, but we should know my other product is copper nitrate, that is CuNO3 2 because it is copper 2 pellets, and then a balanced reaction means I need 2 nitrates and 2 silvers. Now that I've got that, I can start looking at my actual stoichiometry. How many grams of silver? So I'm looking for the number of grams of silver from the reaction of 25 milliliters of 0.35 molar silver nitrate with 0.5 grams of pure copper. So I'm actually going to do two separate stoichiometry problems here. One with the copper turning into silver and figuring how much I can make, and the other with the silver nitrate and turning into silver and figuring how much I can make. It doesn't matter which order I do them in, I'm just going to do two separate problems. So I'm going to start with the 0.5 grams of copper. So with my 0.5 grams of copper, I'm looking for the amount of silver that I can produce, which means I'm going to need the balanced equation and the moles. Stoichiometry is based on mole-to-mole ratio and a balanced equation. So I'm going to take those grams of copper and turn it into moles of copper. That is going to come off the periodic table. 1 mole of copper has a molar mass of 63.55 grams. So I'm grabbing that straight off the molar mass of copper off the periodic table. Then I'm going to take the moles of copper and convert it to moles of silver. Let's see, there it is, copper to silver. This is going to come from the balanced equation. 1 mole of copper will produce 2 moles of silver based on our balanced equation. And finally, I'm going to figure out how many grams of silver, because that's what the question's actually asking. Moles of silver to grams of silver. I'm going to get those grams off the periodic table, and the mass of silver is 107.9 grams per every mole. Is that easy to read there? Sorry, guys. Let's try that again. 107.9 grams of silver per mole. There we go. Okay, so now let's calculate this. When I'm calculating this, I'm going to take 0.5 divided by the 63.55 times 2 times 107.9, and I get 1.70 grams. So based on the copper, I would get 1.70 grams of silver. But that's not my only reactant. My other reactant is the 25 milliliters of the 0.35 molar silver nitrate. So what we remember about molarity is moles over liters. But they didn't give us liters, they gave us milliliters. So my actual first step is changing those milliliters into liters, and that's dividing by 1,000 and 0.025 liters. We're going to divide by 1,000 and get 0.025 liters. So my molarity problem will start like this. 0.35 molar is X over 0.025 liters. This is going to find the moles of silver nitrate so that I can find the grams of silver. So that's 0.35 times 0.025 cross multiplying gives me 0.00875 moles of silver nitrate. From there, I'm going to find the moles of silver and then the grams of silver, exactly like I did with copper. So moles AgNO3 turns to moles Ag, and I'm going to get those numbers off the balanced equation, a 2 for each of them. And then moles Ag to grams Ag. I didn't leave myself a spot for the 1 mole. Let's try that again. 1 mole. And then the mass comes off the periodic table. That is again 107.9 grams of silver. So when I'm typing that in, I have 0.00875 times 2 divided by 2 times 107.9 gives me 0.944. 0.944 grams. So here's the thing about excess limiting stoichiometry. You're going to get 2 separate answers. Hold on, I meant to highlight that. You're going to get 2 separate answers, the 1.70 grams and the 0.944 grams. But one of those answers is real and the other one is imaginary. The real answer is the smaller answer. You can't make any more than your lowest quantity reactant. The not real answer is your larger answer. So this 1.70 grams is not real. It never really existed. It's just theoretical. My answer is 0.0944 grams. Okay, let's try a little bit more to this same problem. The next part of this problem asks how many moles of the excess reactant will be left over from my previous problem. So from my previous problem, first thing I'm going to do is remember what the chemical equation was, which was AgNO3, 2 plus Cu makes 2Ag plus CuNO3, 2. And if we also remember from our previous problem, we actually produced 0.944 grams. Put that in the wrong spot. That was 0.944 grams of silver from our previous problem. So that's how many grams I produced. The question is, how much of the excess reactant was left over? So remember that 0.944 grams came from the silver nitrate, which meant that the copper was the excess reactant. The copper was the thing that was in excess. And so we're actually looking for the amount of copper that we used, was used to make the 0.944 grams of silver. So we're going to do a stoichiometry problem starting from where we ended on the last problem. 0.944 grams of silver, and I'm going to figure out how much copper is used to make that. So grams of silver to moles, that's going to come off the periodic table for the mass of silver, which is 107.9 again. Then moles of silver, and this time we're looking for the excess reactant, which happened to be copper, to moles of copper. I'm going to get those numbers off the balanced equation, 2 for the silver, 1 for the copper. And then moles of copper to grams of copper. And that's going to come off the periodic table. The mass of copper is 63.55. So I'll take my previous 0.944 divided by 107.9, divide it by 2, times 63.55 gives me 0.278. See. But the trick is that 0.278, I'm going to write it again down here, is the grams of copper used to make 0.944 grams of silver. That's not the amount of copper left over. To figure out the amount of copper left over, we start with how much copper we had at the beginning. So we had 0.50 grams of copper initially, and we used 0.278. So if we want to know how much is left over, we will subtract those two. And we get 0.222 grams of copper left. And that is excess limiting stoichiometry. Okay, let's move into percent yield and percent error. Percent yield and percent error have to do with the actual amount of product produced compared to the theoretical amount that should have been produced. So a successful experiment has a percent yield that's close to 100%. If you're really, really good, you'll get 100% yield, although in an actual lab situation that won't normally happen. And a percent error close to 0%. Closer your error is to 0%, the better your lab was. So we have two formulas for that. For percent yield, it's the actual, which is what you made in your lab, divided by your theoretical times 100. And for percent error, it's the actual, which is what you actually made in your lab, minus theoretical, divided by the theoretical. So they are very, very similar, but not exactly identical. Also notice that with the percent error, there is a subtraction sign in the problem, but it also has absolute value bars. So you're going to always end up with a positive percent error. If you get a negative percent error, just make it positive. Your percent error will always be a positive value because it's an absolute value. Let's try a percent error problem. Find the percent yield and the percent error if only 0.75 grams of silver were produced in the previous problem. So if we remember in our previous problem, we were actually able to produce 0.944 grams of silver. But that was our theoretical. From the math, we were supposed to have been able to produce 0.944 grams of silver. But we only, in the lab, were able to produce 0.75 grams of silver. So in our lab, we made less than what we were theoretically supposed to have been able to make. So if we want to find the percent yield, that is the actual amount that we really did make in the lab. That's my 0.75 grams. Usually what you really make in a lab is less than what you were supposed to have made. Sometimes it'll be more because sometimes there'll be impurities or something else in it that you're not expecting. Maybe the filter paper is still wet or something else. But usually your actual amount is lower than your theoretical. Your theoretical amount here is 0.944 grams times 100 to make it a percentage. And we get 79.4% yield. It's also asking us about the percent error. So the percent error is AT&T. Actual, 0.75, minus theoretical, 0.944, divided by theoretical, AT&T. And then times 100 to turn it into a percent. And I ended up with a negative 20.6%, but remember, there is an absolute value bar here, so it actually is 20.6%. So 20.6% error, 79.4% yield. All right, this is our last one. What is the percentage yield of the reaction when 25.8 grams of NaOH react with excess HCl and 34.2 grams of NaCl are produced? So this is a stoichiometry problem. The first thing we're going to need is a reaction. NaOH reacts with excess HCl to produce NaCl, and our other product, which is not listed here but has to be our other product from a double displacement reaction, is water. This one's a really nice reaction because it's a 1 to 1 to 1 to 1 mole ratio, so it's already balanced as is. All I have to do is start throwing those numbers in. 25.8 grams of NaOH and excess HCl, meaning we don't have to worry about how much HCl we have, is going to make 34.2 grams of NaCl, I'm sure, once you've evaporated the water out of it. So that 34.2 is your actual amount. In a lab, I actually produced 34.2 grams of NaCl. I'm going to figure out how much I theoretically should have produced with my 25.8 grams of NaOH, and then from there I can compare my actual to my theoretical. So it starts with just a regular stoichiometry problem. 25.8 grams of NaOH, and we're going to change that to grams of NaCl by getting the molar mass of NaOH off the periodic table. That's 23 for the Na plus 16 plus 1 for the hydrogen is 40 grams of NaOH. Then we're going to convert NaOH to NaCl using the mole to mole from the balanced equation. And here it's just 1 to 1, and it feels like this step is unnecessary, but you always want to include it, and so you're making sure you're paying attention to that mole ratio. And then finally, moles of NaCl to turn into grams of NaCl. That's 23 for a sodium plus a 35.5 for a chlorine is 58.5 grams for the molar mass of NaCl. So I'll take my 25.8 divided by my 40 times 58.5, and I ended up with 37.7 grams of NaCl. Now that is my theoretical NaCl. I theoretically were supposed to have made 37.7 grams of NaCl. I actually made 34.2. So for my percent yield, it's my actual, which is 34.2, divided by my theoretical, which is 37.7, times 100 to turn it into a percentage. And I end up with 90.7% yield. Ooh, I did a good job on this lab. Again, it is possible to end up with a greater than 100% yield. Not that you've actually made more than you could make, but maybe particularly in this experiment, you were drying off or evaporating the water. Maybe you didn't evaporate all the water, so your mass of NaCl at the end seemed to be higher than it should. So a higher percent yield, over 100%, doesn't necessarily mean you did greater than 100. It just means you kind of messed up going the opposite direction. All right, well, that was excess limiting stoichiometry and percent error and percent yield. I'll see you guys next time.